Hello, welcome back. So today we'll be talking about the idea of writing energy and momentum using information in the configuration space, that is the generalized coordinates. That's why I called it generalized energy and momentum. Although we should note that we are not generalizing the concept itself, we are just writing same concept, kinetic energy, in this video as a function of our generalized coordinates. So that is the goal of our work. And we have seen before how we can describe a system with generalized coordinates, how we can define virtual displacement that are consistent with the constraints within the system, the concept of virtual work, and the principle of virtual work. And this lecture is just a natural progression of same ideas. All right, the first one is kinetic energy that we want to discuss. To do that, let's consider a system of particles. So I have system of n particles. And that's in 3D. So in that, I will have three n Cartesian coordinates. And let's also take the system. We have n generalized coordinates. Let's call these xk, where k is from 1 to 3n. And let me write it down. Generalized coordinates qi. So I have x1, x2, x3 are the coordinates of the first particle, particle 1, x4, x5, x6 is the second particle, and so on. And we have some arbitrary choice of whatever the generalized coordinates would be. Okay, we know if I have these Cartesian coordinates, the kinetic energy is rather simple to write. It's 1/2 mv squared, and v squared is the speed of each particle, which is x dot 1 squared plus x2 dot squared plus x3 dot squared for the first particle. So summing all of them over the entire system is k equals 1, 2, 3n mk xk dot square. And here note that m1 equals m2 equals m3. These are mass of particle 1, and so on. So that is our kinetic energy. The goal is to write this as a function of our generalized coordinates. So as a function of essentially q dots. So to do that, we use the transformation equation. Transformation equation that we have. So each of these coordinates, xk, which could be possibly a function of q and time. We have this transformation equation. From this, we can get x dot k. X dot k is going to be sum of partial xk, partial q. Do I have I or j? I. Q dot I, and possibly function of time, so partial xk, partial time, when I is from 1 to n. So I have this, and I can plug this definition of x dot k into that. And when I get is T is 1/2 sum of K1, 2, 3, N, all my actual coordinates, MK, and that thing is squared. Sigma I equals 1 to N, partial XK, partial QI, Q dot I, partial XK, partial T squared. So we have a lot of terms here. So I have n terms or n plus 1 terms added together and then squared. And then I have 3n version of that. So I have a lot of terms. So if you group them together and first do the squared and then add them together, and then if you want to try to group them together, it's going to look something like this. Which this one, I'm just going to follow my notes so I don't miss anything. Sum of I equals 1 to N. Sum J equals 1 to N. Mij Q dot I, Q dot J, plus sum of a big sum this is I equals 1 to N, sum of K equals 1 to 3N, MK, partial XK, partial QI, partial XK, partial T, dot Q dot I, and one last term plus 1/2 summation K equals 1 to 3N, MK, partial XK, partial T squared. Okay, a gigantic equation. There are a few things that are actually unknown yet. So what is this Mij? Let's define that. Mij, which is the same as Mji, is sum of K equals 1 to 3N, Mk, actual mass of a particle, times partial xk, partial qi, partial xk, partial qj. So let's have this in mind. Now let's unpack what is going on. So the first term, this one, if you can't see my cursor, is really the kind of kinetic energy that we used to be familiar with. A bit generalized, or written in terms of generalized coordinates, and that is 1/2 of all kind of partial masses times velocity is a square. And this Mij or Mji is essentially some effective inertia that is associated with the direction or the coordinate qi and qj. So I want to draw an analogy. So for a single, analogy. For a single particle, we had T equals 1/2 mv squared. So from here, we can see m is actually the second partial derivative of T, kinetic energy, with respect to v. Similarly here, Mij is the second partial derivative with respect to qi, q dot i, q dot j. So these are the effective inertials that are acting at the intersection of these two directions. And we kind of expect that MII, which is inertia along one of these principal axes of QIs, would be very similar to the mass. And it turns out it is mostly mass. So if it's a rotational coordinate, we have more or less moment of inertia. And if it's a linear, we have something with the unit of mass. What else? So that is the first term. The second two terms in the T definition have the term partial x, partial t, and those show up only in cases that we have these explicit notion of time in our transformation equations. So you can imagine in our transformation equation up there, there is some kind of driver, like I had the example of a hydraulic jack that changes the length between two particles. So if those kinds of drivers don't exist, so let me write it down. No, before that, so these two long terms in the definition of kinetic energy are because of those explicit influence of time in our transformation equations. They cannot be ignored in general, but if T does not show up explicitly in transformation equation, EQs, in this case, partial xk, partial t is 0. So both of these terms will cease to exist. And what we are actually left with is t is a rather nice form, 1/2 I equals 1 to n, partial j equals 1 to n, mij, q dot I, q dot j. So that's a very well formatted equation for the definition of kinetic energy written in terms of generalized coordinates. Let me see if I'm missing anything. Let me also keep that because it's a nice looking equation. What else? I have covered everything. And one last thing, if you recall from I think it was last video, that we defined something called gamma ki. It was the sensitivity of velocity, actual velocities of particles relative to velocities in the generalized coordinates. So partial v k, partial q dot I. And with this definition, you can work out the details. I'm not going into the short derivation. Mij will be summation over all particles. So k equals 1 now to n, summing over all particles. Mk gamma ki dot gamma ik. And remember, gamma ki and ik are different things. And using this, we can also write the, I don't have it. Do I have it? I don't have it in my notes. Yeah, that's good enough. You can also write the kinetic energy in terms of these gamma terms. I don't write it down because I don't have it on my note, and I made a I might make a mistake. But anyways, these are gammas, these are not R's. So these are the definitions of kinetic energy using information in the configuration space or using generalized coordinates. Maybe to give you better intuition, let's look at a very simple example. Extremely simple. So I have this 2D space, a particle that is kind of constrained with a rigid link. That's not nice. To be a certain distance from the origin, so that is L. We know I can easily describe the system by these generalized coordinates of the angle. So I have x and y as my two Cartesian coordinates, and the angle theta being the generalized coordinates. So from before trying any of these fancy equations, we know that t is 1.5 m, it has mass m, v squared. And because it's pure rotation, the velocity or the speed is LQ dot, so it is going to be LQ dot squared, or I can write it slightly nicer, 1/2 ml squared q dot squared. So we already know the answer in terms of q dots, but let's try to derive it. I'm using the equation we have. So let's call my x1 to be the x coordinate, which is L cosine of q, and my x2, which is y, is L sine of q. And just for the sake of generalization, x3, which is my z, let's call it 0. So these are my coordinates, partial x1, partial q. Taking derivative of that is minus L sine of q, partial x2, partial q is L cosine of q, and partial x3 over partial q is 0. So I only have one particle and one generalized coordinate. So the mass equation is relatively simple. So I only have m essentially 1, 1, because I only have one generalized coordinate. And by the definition, sum of k equals 1. And let me write it down. M1 equals M2 equals M3 equals M. These are the masses. So I have 2, 3, n, where my n is one particle, so n equals 3, and actually the last coordinate is also along z, which is 0, so even up to 2 would work. And mk partial xk partial qi partial xk partial qj. So let's break out or spread the summation. I have m1 partial x1 partial q1, which is just 1. I'm writing 1, 1, so this has to be actually 1 and 1, or q and q. Partial x1 q squared plus m2 partial x2 partial q squared plus m3, let me write it down, partial x3 partial q squared. So this one is 0, what we have is m1, which is m. Partial x1, partial q is minus L sine of q squared plus another m L cosine of q squared, which is ml squared sine of q plus sine squared q plus cosine squared q, which this one is 1. So my kind of generalized mass along this direction of q turns out actually to be the moment of inertia. So that's how you can see these fancy math equations actually end up with very tangible results, and they mean something. And from here, my kinetic energy is 1/2 summation of, I only have one coordinates, so j equals 1 to 1, mij q dot I q dot j. So it's only one term, and that is 1/2 m11, which you could just calculate it, ml squared q dot squared. And that's how we got the same equation for the kinetic energy of the system. So we did this because it was easy. We could easily think and write equations. But in general, when we have a complex system, this method often becomes not infeasible, but very tedious to do by hand. And a systematic way to calculate these energies are very important in both modeling and for other analytical methods. All right, so that is all I have for this video. In the next 2 videos, we'll talk about other concepts of potential energy and conservative forces, and we'll do conservative generalized forces and momentum. So until then, I'll see you soon.